Okay, assignment 7, question 1a. We are asked to solve the differential equation dy by dx is equal to 1 minus y to the power of 2. This is a simple separable differential equation, so we can bring all of the y terms to the left-hand side as such, and still have dy by dx left over, and that will be equal to 1. And then what can we do? We can integrate both sides of that equation. So integrating the dy dx, these two, they don't cancel, but it's the same as integrating dy. So this is the same as 1 over 1 minus y squared dy is equal to the integral of 1 dx. So integrating this, we find that the solution will be 1 over 1 minus y. So what have we done? We've increased the power from minus 2 to minus 1, divided through by minus 1. So you'd say y no negative, because there's also a minus in front of the y. So we divide through by the constant derivative of y. So the two negative signs cancel out. And then on the left-hand side, we get x plus some arbitrary constant of integration. Making y the subject, because we're told to make y the subject of this one, we know that 1 minus y will be 1 over x plus c, and so y is 1 minus 1 over x plus c. We now need to draw this for differing values of c. What does this look like? Well, I'll have GeoGebra help me out a little bit here. You can see this is what it looks like for c equals to minus 1. As I increase c, you can see that it's moving the graph to the left. And similarly, as I decrease c, it moves the graph to the right. All of these graphs have a few similarities, however. They will have an asymptote at negative c. X equals to negative c. So you can see here where c is 3, there is a vertical asymptote at negative 3. And all of them have a horizontal asymptote at y equals to 1. There's something very interesting that we can look at here as well. From here to here, we've made an implicit assumption. We have assumed that y does not equal to 1. And what you actually find is that that's not necessarily a fair assumption to make. In fact, y equals to 1 is a constant solution, and I'll leave it to you guys to verify that by substituting the function y equals to 1 back into this original DE, it does satisfy it, and that this is actually a solution curve. But I'll leave that to you guys. Alright, let's take a look at another one. Let's take a look at 1b. 1b, we have to find the general solution to the differential equation 9 minus x squared squared d2y dx squared minus x equals to 0. So in other words, this is a second derivative, a second order differential equation, so because of the second derivative there. So what we want to do is we want to just integrate it with respect to x 2 times. So how do we do that? Well, the first time is not too bad. This is in the form f prime of x is over f of x. F prime of x times f of x to the power of minus 2. So the first derivative, not thinking, trying to talk and think at the same time, not really working. So dy by dx, that's integrating the left-hand side, will be the integral of x over 9 minus x squared squared dx. You can kind of think of that like the integral of minus 2, or negative a half, times the integral of 2x, negative 2x, sorry, 9 minus x squared to the power of minus 2 dx. So you can see we've got the derivative of the x squared here, so we just have to increase the power by 1, so that this is going to be negative 1/2 the integral of 9 minus x squared to the power of minus 1, and there's a negative sign here as well, dividing through by the new power. So in other words, that this is just 1/2. Oops, why did I still have an integral sign there? Sorry, I shouldn't have had that. 1/2 9 minus x squared to the power of minus 1 plus our constant of integration. Okay, so that's dy by dx. What about y? To find y, we just integrate this again. This will be the integral of 1/2 1 over 9 minus x squared plus c dx. Now this one we recognize, this is something we can do by partial fractions if we like, but we also have a formula to evaluate 1 over the difference of squares. So we get 1/2 times 1 over 2 times 3 ln, and because this is 3 squared, and then you get 3 plus x over 3 minus x. Please remember the absolute value signs. We're integrating a constant c, so this becomes cx, and then we get another constant d. Please make sure you use a different variable. This d is not the same as this c here. So this is the solution to 1 part b. What about 1 part c? So 1c. 1c, we need to solve the differential equation dy by dx is equal to x cubed y minus 1. So again, this is a separable differential equation because we can bring the y's to the left and leave the x's on the right, but this will require us to find a particular solution because we're told y equals to 2 when x equals to 1. So bringing that over, what do we get? We get 1 over y minus 1, the integral thereof, dy is the integral of x cubed dx. In other words, ln mod y minus 1 is equal to 1 over 4 x to the 4 plus a constant of integration. I quite like to keep going before trying to substitute this in to find the constant c. So that's what I'm going to do. Mod y minus 1 is equal to e to the c, e to the 1 over 4 x to the power of 4. Y is equal to 1 plus a e to the power of 1 over 4 x to the 4, where a is plus minus e to the power of c. So now I substitute in because I've got rid of my plus or minus. When x equals to 1, y equals to 2, so 2 is equal to 1 plus a e to the power of 1 over 4, and we see that a is equal to e to the power of negative 1 over 4. So therefore, our final answer is y is equal to 1 plus e to the power of 1 over 4 x to the power of 4 minus 1 over 4. And that's our final answer. For question 2, we're given this differential equation, dy by dx is equal to 1 minus y over x plus xy squared. And we're told to use the substitution z is equal to xy to show that it reduces to something in just z. So, okay, we can do this. Given this expression, the substitution, I first want to know what is dz by dx using the product rule, that is y plus x dy by dx. Okay, and what about over here? So, in other words, this means that dy by dx is equal to 1 over x dz by dx minus y. Excellent. So now I can get rid of, sorry, I've got a y here, I don't particularly want that. That's going to be 1 over x dz by dx, and y you can see is going to be z over x. So, okay, now I've got dy by dx in terms of only z and x. So what about over here? I'm going to get rid of all of my dz by dx. I'm going to get rid of all of my y, replacing it with z over x. So I get 1 over x dz by dx minus z over x is equal to 1 minus z over x plus x z over x squared. Okay, a little complicated. Let's just hang with it for the moment. I'm going to try and make dz by dx the subject of my equation. So this is 1 minus z over x. Expanding that, I get z squared over x. You see there's a divided by x everywhere, so I'm just going to cancel that out. So I get dz by dx is minus z over x is equal to 1 minus z over x plus z squared. Going to cancel those out. Dz by dx is 1 plus z squared, which is what I wanted to show, so we're happy. Right, what can we do with this? We can now solve this. We recognize this as a simple separable differential equation. So the integral of 1 over 1 plus z squared dz is the integral of 1 dx. So therefore tangent inverse of z is equal to x plus c. Z is equal to tangent x plus c. But we aren't told this in terms of z, we're told this in terms of y and x. So we substitute back in and we find that the final answer is y is equal to x tangent x plus c. Sorry. Oops. Sorry. Z is equal to, I got that the wrong way around. Xy is equal to tangent x plus c, so y is 1 over x tangent x plus c. Question 3 gives us a word problem. In a large fishing pond, there is an initial population of 6 million fish. So it tells us the population is p later on. So when t equals to 0, p is 6 million. Okay. It is found that the annual natural growth rate of the fish population is 5% of the population at that time in years. So let b denote the number of fish born. Then we are told that the growth rate dB dt is 5% of the fish population. Okay. In addition, k% of the fish population is lost due to fishing activity. So let d denote the number of fish lost. That tells us that dd dt is k over 100 p. Write down a differential equation relating p and t. So we know, therefore, that the change in population with respect to time, that's going to be the number of fish born, subtract away the number of fish who got caught. So that's going to be 5 over 100 p minus k over 100 p. That's going to be 5 minus k over 100 p. So solve this differential equation, find the value of k such that the fish population will double after 50 years. So now we want to solve it. This is a simple separable differential equation. We can move the p to the left hand side and we get the integral of 1 over p dp is equal to the integral of 5 minus k over 100 dt. So solving this, we get ln p is 5 minus k over 100 t plus some constant. That p is equal to ae to the 5 minus k over 100 t, where a is e to the power of c. So now we come back to our initial conditions. When t is 0, p is 6 million. So therefore 6 million is ae to the power of 0. That means that a is 6 million. We want the population to double in 50 years. So when t is 50, we want p to be 12 millions. So that means we get 12 million is 6 million e to the power of 5 minus k over 100 50. And we can solve that. So we get 2 is equal to e to the power of 5 minus k over 2. That gives us ln 2 is equal to 5 minus k over 2. That k is equal to 5 minus 2 ln 2, which is approximately equal to 3.61 to 3SF.